Happy day to you all. This is Orekoya Olusegun, Physics Mathematics Fundamentals on YouTube. Today, we are going to employ calculus to derive the area of a circle. Please don't forget to like, share, and comment on my video. Thank you. This morning, we are going to derive the area of a circle and circumference of a circle by calculus method. Now, let's consider a circle and let's think of a point moving along the circumference of that circle. Let's say the point is at position P1 here. As the point moves to another position, let's call it position P2. As the point moves along this circle, it describes an infinitesimal portion, that means a very tiny portion of the circumference called the C. As this particular movement describes this DC, we can notice that the radius of this circle is also moving as the point is moving from P1 to P2. As this happens, there is an infinitesimal change in the angle between the radius at position P1 and position P2. Now, if we bring this portion of the circle out, we can have something like this. Something like this. That's a sector of a circle. This is the infinitesimal portion of the circumference. That's the arc. So we have the T. That's the angle subtended at the center. Now, I want to derive the area of the whole circle. How do we do that? One condition is that our calculations of the angles will not be in degree but in radian. And then the conversion between degree and radian is that 360 degree equal to pi radian, angle in radian. We should note that. Now, because this particular sector is very small, the portion of the circumference, this arc is also very small, and it can be approximated to a straight line. So this my DC can be taken as a straight line because they are very, very small, tending towards 0. So in a nutshell, my sector can be written, can be constructed to look like a right angle triangle. So I can have this place as my infinitesimal height of my triangle. This DC. The radius remain the same. Then the angle, the theta. Now, we know that area of a triangle, this small triangle, because it's a small area, we can say the area is equal to R base times height. R base times height. The base here is the radius of the triangle. So we have it as R times the height. That's our DC. How do we get this DC? We know that we can say tan d theta is equal to DC over R. So this implies that by cross multiplying R d theta, R tan d theta is equal to DC. But we should know something. Tan d theta is very small and is approximately equal to 0. The theta too is a very small quantity, and I can equally approximate it to the theta. So in a nutshell, tan d theta, tan R d theta, R tan d theta can be written as R d theta. So my DC will now become R d theta. I can now put this in the area of the circle. The A will now turn to half R times R d theta, which is 1 over 2 R square d theta. That is the A. Now, in order to get the total area of my circle, I need to sum up this small tiny area, the A. What do we do on that? We integrate. Integrate simply means summation. Summation of infinitesimal quantity is what integration is all about. So integration of the A will give us the very big A that we are looking for. Now, half r square is a constant, so I can put it outside the integration sign. R square all over 2 integral d theta. Now, the total angle in a circle is 360 degree. And to write this in radian, we write it as 2 pi radian. So my summation for the angle now will be from when the angle is 0 and when it completes 2 pi. That means when the angle is 0, the radius has not moved at all until the radius now move from position P1 and cover the whole circle. As the radius move from position P1 and cover the whole circle, the angle here will become 2 pi. So that's the idea of the limits of our integration. So in a nutshell, when you integrate the theta, we have theta. So I'm having r square all over 2 theta 0 to 2 pi. This will be our limit. Now if you put 2 pi here and you put 0 here, because this is 0, everything here will be 0. So 2 pi minus 0 is same thing as 2 pi. So substitute 2 pi into the theta. We have r square all over 2 times 2 pi, which is equal to, the 2 cancel the 2. So I'm having my area now to be equal to pi r square. That is one aspect of what our discussion here is. Now, to get the circumference of that circle, we can still use my sector, this particular sector that I have here. We know very well that the sector, this length of a sector, length of an arc of a sector, length L, we know is theta all over 360 2 pi r. In radian, the length of the arc of a sector is 2 pi. That's in radian. This my 360 become, the 360 become 2 pi. So we have 360 times 2 pi r. So the length now become theta all over 2 pi times 2 pi r. So 2 pi cancel 2 pi. So the length of that infinitesimal arc, that is the C, is now theta r. Or we can write it as the theta r. That is the C is equal to the theta r. So we can rewrite it as the C is equal to r d theta. So integrating the C is actually total circumference of the circle. Whatever we do to this side of the equation, we do it to the other side. So integrating r d theta. And our limit is from 0 to 2 pi. Now the r here is a constant. We can put it outside the integration sign. So I have r integral 0 to 2 pi d theta. Integration of d theta is theta. So I have r theta. Then we put the limit 0 to 2 pi. If we substitute this limit here, 2 pi, if you substitute 2 pi for pi, we have 2 pi. Take away 0 into 2 pi, that's take away 0. So everything here will now be r times 2 pi, which is 2 pi r, the circumference of the circle. Thank you so much.